previously, a transaction conflicts with another transaction or with non-transactional code if they access the same cache block and at least one of them is a store. And at least one of the two transactions are aborted. Now, there is a thing which one must know about the power architecture, and it is that the cache block size is not specified by the architecture, but instead by the user manual of a certain chip. And the reason for that, of course, is that different markets may need different cache block sizes, so it should not be fixed. But the software must take this into account, since it otherwise can be a disappointing surprise. Okay, a transaction can be in, or a thread can be in three different states. Non-transactional, which is the normal, or transactional between begin and end, and suspended. And that is when it is in a begin, I mean it's between begin and end, and it has executed this suspend instruction and not yet executed the resume instruction. Okay, so why do we have this state? It is for some things which cannot be rolled back at a transaction failure. For instance, communication, or I/O, or simply debugging to let the debugger print out the value. Also, but not very common, not for normal application programs, to access so-called non-cacheable memory. That is memory addresses which always skip the cache. Okay, so what happens if we access data that the transaction also has accessed from within the, if we access the same data as in the transaction and in the suspended part? There can be some confusion, and there is even a warning in the power instruction set architecture documentation. Okay, so let's write this in some symbolic assembler. Okay, so let's assume that we first set to, all assembler is symbolic, but some kind of pseudocode. So we set the variable to 0, start the transaction, set it to 1, and then suspend, and then increment x. What happens when we increment x? Well, what should it be? If we take this 1 into account, then the value of x should be 2. But this write in suspended state will kill the transaction. Okay, so this write will not last very long. And what is then the result? It's actually 2. And this is, in a sense, non-intuitive, since we incremented, we started with 0, and then this never happened, so to speak. It was rolled back, and then we incremented, so it should be 1, or at least 1 more than it was before. But it will end up as 2. Okay, so you can read this from the documentation. Well, I can read it. Accessing storage locations in suspended state that have been accessed transactionally has the potential to create apparent storage paradoxes. It must be used with care. Yeah, that's a good idea.